Okay, video 2 on the rates of change in the natural and social sciences, 3.7 in your book. Last video was a lot of explanation. I went slowly through one example. We kind of ran out of time. So let's just go ahead and pick right back up. As promised, I'm going to be doing problems that are actually out of your textbook. And I'm going to start with number 8. For those of you that do not have your textbook on you, I will try and read it slowly and carefully and actually put the relevant information down on the paper so we can all follow along. Number 8 says, if a ball is thrown vertically upward at a velocity of 80 feet per second, so a ball is thrown up at 80, what is that, feet per second, okay? Now, and then it says, then its height after t seconds is, well, we should remember that this is, oh yeah, sorry, that's supposed to be a t in there as well. Okay, so in order to gauge the height of a particular projectile, basically it's -1/2 the pull of gravity times time squared plus the initial velocity times time plus the initial position. Okay, now they didn't actually expect you to do that. They actually gave you the model in this particular one and gave it to you as 80 t minus 16t squared because it's feet, and gravity according to acceleration of gravity according to feet is 32 feet per second and therefore 32 times -1/2 gives you your -16. Your initial velocity is 80 feet per second, and since there's no constant term, it's assuming that the initial position was 0. Okay, so it was thrown up at time 0, it was at ground level, and then it was thrown up at 80 feet per second, and you can find its height at any time t using this little thing right here. And the part A says, what is the maximum height reached by the ball? Well, here's the thing. This ought to sound awfully familiar, because up to now, they haven't really asked you any questions that can't be arrived at by means of Algebra 2 and Pre-Cal methods. Okay? Now, it may have been a little while, but this is a downward-facing parabola. Its maximum is going to be its vertex. So if I actually wanted to do this Algebra 2 style, just pull out the -16, and I get 2 squared minus 5t plus blank, right? And I need to go ahead and complete the square. 5 halves squared, 25 fourths, okay? 25 fourths, well, that's not really 25 fourths, that's really -100, right? And so I have to add 100 in order to compensate for that. And what this really winds up being is, in vertex form, it winds up being that, okay? So what is the maximum height reached by the ball? Well, the maximum height is 100. If it asked you when did it reach its maximum, that would of course be 5 halves, right? At time t is equal to 5 halves, or 2.5 seconds, it reaches its maximum height of 100 feet. Now, that would be how to do it in terms of Algebra 2, but let's go ahead and do it using calculus. If I take the derivative and I get 80 minus 32t, now why did I take the derivative? Well, I happen to know that the ball is going to reach its maximum height when its velocity is 0, right? Because by definition, if the velocity is not 0, then it hasn't stopped going up and started to come down. It's either still going up or still going down, right? You know that, if you throw a ball up, as long as it's on this side right here, okay, its velocity is positive. Here, the velocity is negative, 0, and down here, the velocity is negative. So in order to actually find out when you're going to wind up with a velocity of 0, you just set it's an output-based question for the velocity function. Hello, Mr. Velocity Function, when are you 0? Well, I'm 0 at 5/2. And then I would just take 5/2 and plug it back into here. Now, that winds up being 200 minus 100, or 100. Now, you're thinking to yourself, well, gosh, it's just easier to do it with the Algebra 2 way. Why in the world am I actually learning how to do it by the calculus way? Well, you're only capable of doing it Algebra 2 way if it just happens to be a velocity and acceleration question due to gravity, and therefore necessarily a parabola. If the function that you're given in terms of projectile or particle motion is not a parabola, if it's not a quadratic, well, good luck, because completing the square is an Algebra 2 thing, but the rest of the models that you're given, the rest of the scenarios, with the exception of these particular scenarios due to gravity, will not be in terms of that. Okay, but it also asks in part B, what is the velocity of the ball when it is 96 feet above the ground on its way up, or on its way down? Okay, well, here's the thing. In order to measure velocity when the ball is at 96 feet, I have to determine what values of t are associated with that height. Okay, so this was part A. Part B, we got to go ahead and set our function, which is 80t minus 16t squared, and we need to set that equal to 96. Well, let's go ahead and shove all of that over on one side. Let's go ahead and divide through by 16, because I can. Okay, and I notice that this factors very, very easily, and apparently the projectile, or the ball in this case, is at 96 feet at 2 times. Well, that makes sense. If this is 100 feet, then that's 96 feet. It's going to hit 96 feet on the way up and on the way down, right? Well, look at those times. T is equal to 2 and t is equal to 3. Well, those are equidistant in terms of time from 2.5. And that shouldn't surprise us because of the symmetry of parabolas. Now, if the times are symmetrical, it stands to reason that the velocities will have some sort of symmetry about them as well. And so s prime of 2, which is basically v of 2, right, is 80 minus 32 times 2. And s prime of 3 is 80 minus 32 times 3. This is 80 minus 64, which is, of course, 16. This is 80 minus 96, which is negative 16. And, of course, we'll go ahead and put in the obligatory feet per second, right? So it makes sense, and of course, the symmetry of the parabola sort of helps us reason it out and confirm the fact that those are indeed answers that make sense to us in terms of the scenario that's given to us. Let's go ahead and skip from number 8 on over to number 14. 14 is a little bit different. Okay. 14 asks us the following, or gives us the following scenario. A stone is dropped into a lake, creating a circular ripple which travels outward at a speed of 60 centimeters per second. Okay? Now, that's saying, okay, a stone is dropped into a lake, creating a circular ripple that travels outward at a speed of 60 centimeters per second. Well, I've got news for you. If it travels outward at a speed of 60 centimeters per second, then that is how fast the radius is changing with respect to time. Okay? Now, it asks, find the rate at which the circle with the area within the circle is increasing after 1 second, 3 seconds, and 5 seconds. Well, I've got news for you. I don't like, one of the reasons that I do not like this particular section is because this is actually much easier to do in terms of related rates, which is 3.9. You have to do a whole lot of hop, skip, and a jump in order to sort of get it such that, yeah, I just don't really like it. Because you have area is pi r squared, right? And we're used to the fact that that basically we differentiate this with respect to r, right? But your radius, your area isn't changing with respect to the radius so much as both your area and your radius are changing with respect to time. So what happens here is I'm taking an equation of two variables, and I'm differentiating it with respect to a third, okay? And this winds up giving me dA dt, the rate at which area is changing with respect to time, is equal to 2 pi r dr dt. Okay? Isn't it kind of interesting that when you go from 2 dimensions down to the first, the area turns into the circumference formula right here? That is rather interesting. Now, I know I've been told that dr dt, okay, this is 60 centimeters per second. Okay, so actually this winds up being 120 pi r, so the area is increasing at a basically a constant, basically this is a direct variation question, right? The rate at which the area increases with respect to time varies directly with the radius. So all you have to do at this point, when it says find the rate at which the area within the circle is increasing after 1 second, well, the rate at which the area is increasing after 1 second, see, you would have to go back and find the r that's associated with that. The r that's associated with 1 second is, of course, 60. The r that's associated with 3 is 180. The r that's associated with 5 seconds would, of course, be 5 times 60, because those are radius measurements, and you know that the radius is increasing at a constant rate of 60 centimeters per second. So it would be 120. So, you know, part A would be dA dt is equal to 120 pi times 60, okay? Part B, dA dt is equal to 120 pi times 180, and C would be dA dt is equal to 120 pi times 300. And of course, I'm not a very good science person, since I, haven't put the units on there, okay? Because already centimeters per second is included in this 120 pi, and therefore, this is centimeters squared per second, centimeters squared per second, and centimeters squared per second. Now, I'm sure there is a way to bend over backwards to make sure that this does not wind up being a problem where you have an equation of 2 variables that you have to differentiate with respect to a third. But, it's very hard to sort of unthink that mode of thinking once you've learned it, and therefore, and there's really no reason to not work this problem in that particular way. Another reason why I don't like 3.7, but this problem, I think, is trying to foreshadow 3.9, and therefore it's not illegitimate in that sense. And of course, you would just plug this into your calculator, or just, do the multiplication and keep the pi. But remember, if you're going to approximate it using your calculator, the AP graders want 3 decimal places, rounding to 3 decimal places, which is why we've been rounding to 3 decimal places ever since I gave you your calculators back at the end of your Algebra 2 year. Okay, now that brings us to about 15 minutes. as per usual, I didn't get through nearly as many questions or problems as I wanted to, but I will go ahead and spend the next video doing a couple of more particle motion problems, because those are the ones that really are kind of the bread and butter of just your initial application of the derivative towards the physical sciences, particularly physics. Okay, so look forward to that on video 3.